Hey guys, welcome back to lecture series on numerical methods for our solution of a differential equation. So already I have explained plenty of the methods here in our channel, like Euler's method, modified Euler's method, Runge Kutta second order method, Runge Kutta fourth order method, okay, with some of the examples. Okay, so here in our today's video guys, I am going to explain Runge Kutta method, okay, that we are going to use it for the solving simultaneous differential equation of the first order. Okay, simultaneous differential equation of the first order. So see that already we have learned dy by dx is equal to f of xy as a first order differential equation. Okay, but now right now we are having symmetrical simultaneous differential equation for first order. Okay, so let's see, we are going to understand the concept once our lecture start. Okay, so without further ado, let's get dive into our today's lecture. We're going to understand the simultaneous differential equation first. Okay, yes, now until we till this moment we learned to solve dy by dx which is equal to f of xy. Okay, this is only the simple time differential equation. Okay, dy by dx which is equal to f of xy. Okay, so for solving this one we learn Euler method. Okay, Euler's method, second modified Euler's method. Okay, modified Euler's method and Runge Kutta method. Okay, Runge Kutta method. Okay, it is for second and fourth order that we learn for solving simple differential equation like a dy by dx which is equal to f of xy. Okay, but now what is meant by simultaneous differential equation? Okay, that means the two differential equation involve at once. Okay, two differential equation involve at once, then we need to find out their solution. Okay, that means simultaneous differential equation. Let me explain simultaneous differential equation. Okay, consider, okay, let me consider here consider simultaneous differential equation. Okay, consider simultaneous differential equation. So simultaneous differential equation means we consider dy by dx which is equal to f of xyz as a one of the function for three variable f of xyz, and another differential equation consider dz by dx. Okay, dz by dx. Okay, consider some another differential equation dz by dx as a g of xyz, g of x comma y comma z. Okay, this type of the differential equation we consider it as the simultaneous differential equation. Okay, so I hope concept it is clear for you all. Simultaneous differential equation, these look like this way, this is way. Okay, this is f of xyz function in a three variable, and g of xyz is a differential equation in a three variable. Okay, dz by dx. Okay, yes, I consider dy by dx and dz by dx as a two differential equation. Okay, now see that as we have single differential equation dy by dx as f of xy, we consider it is the initial condition y of x naught which is equal to y naught. Okay, every differential equation possesses at least one boundary condition. Okay, or initial condition. Similarly, that one also having one initial condition, and that one too. Okay, so yeah, we are having two initial condition here. Okay, so what we have here, first we have y of x naught which is equal to y naught for this one. Okay, so you consider some another initial condition for these two one. Okay, so consider this one as y of x naught which is equal to y naught. Okay, y of x naught which is equal to y naught as a first initial condition. Okay, and another initial condition you consider the function in the form of z. So we consider z of x naught which is equal to z naught. Okay, z of x naught which is equal to z naught. This function has initial condition, and this function has this one is as initial condition. Okay, so we have these two initial condition. So with respect to these two initial condition, we are going to define the Runge Kutta method for the solution. Okay, so here x is independent variable and yz are the dependent variable. Okay, so you can see here x is a independent independent and y comma z dependent. Okay, so what is mean by independent and dependent, that already I explained in my first unit. Okay, solution of differential equation. Okay, in our first unit I already explained. So if you are interested to see this concept, go and check these videos, guys. Okay, so here we have x is independent, y is a dependent variable. Independent means the variable which is not dependent on anyone else. Okay, dependent means the variable need to be dependent with someone else. Okay, so see that dy by dx. Okay, so I'm going to explain dependent here. Okay, see that this x, it is not dependent on anything else. Okay, but y, we can see that y is, we are taking differentiation of y with respect to x, that means y, it is dependent on x. So here we have y as a dependent variable and along x as the independent variable. Okay, so that I hope you have understood what is the independent and dependent. Okay, so see that y and z both are the dependent, where x, which they are dependent on x here. Okay, and x, it is the independent. Okay, I hope you all understood the dependent and independent. For more detailed video, guys, you can refer to my channel. Okay, for previous videos. Okay, so let me explain the point that we needed here. Okay, yes, the starting point we are going to consider for our starting initial condition. Okay, for our first iteration we are going to consider starting initial point as a x naught comma y naught comma z naught. Okay, we are going to consider x naught, y naught, z naught as a starting point and increment as a step size for x, y, z. Okay, so for x, for y and for z we are going to consider step size. Step size means in our previous Runge Kutta method we consider h as absolute difference or the step size. Okay, that we have to let me write this one first. X naught, y naught, z naught, it is the starting point. Starting point. Okay, these are the starting points. Okay, and a step, a starting point. After that starting point means step size or increment, that we consider it as the difference. Okay, we as to consider absolute difference, we consider this one. Okay, as a h, that in our previous Runge Kutta method. But as we have three variable, we'll get the three step size or three difference. Okay, like x naught has h, y naught has, consider any variable. Okay, y naught has k and z naught has l. Okay, these are the step size. Okay, it behave like our first previous h from our Euler method for second, fourth order. Okay, yeah, that we apply for our simple differential equation. Okay, yes. So now these are the basic prerequisites here that we needed for defining second order Runge Kutta method or fourth order Runge Kutta method. Okay, yes. So let me write the second order Runge Kutta method and fourth order Runge Kutta method. So in our simple differential equation we consider k1 as a h into f of x naught, y naught. Okay, this one I'm going to write for Runge Kutta formula for second order. Okay, Runge Kutta formula for second order. This is the Runge Kutta formula for second order. Okay, yes, that I'm going to define it here. Now see that in our simple differential equation we consider k1 as h into f of x naught, y naught. Okay, but instead of f of x naught, y naught, we have another variable z also introduced and another function g also introduced. Okay, so I'm going to write for our first iteration k1 as h, keep as it is, not going to change. F of x naught, y naught, we are going to write f of x naught, y naught, z naught. Only third variable I introduce here. Okay, yes, k1 as f of x naught, y naught, z naught. Okay, similarly k2. Okay, similarly k2 I am going to write. Okay, so k2 we know that f of x naught plus h by 2, y naught plus k by 2. Okay, that we have to replace here only. Okay, Yes, so we are going to write h multiplied by f of x naught plus h by 2 y naught plus k1 by 2, and we have third more variable z naught plus, or you consider it as the L1 by 2. Okay, x naught plus h by 2, y naught plus k1 by 2, z naught plus L1 by 2. Okay, yes. So this one is the value for k1, this one is the value for k2. So most of you all are thinking, oh sir, we will get that k1 from here, h, it is already the step size there, all the values are given, but what about for the L1? Okay, so L1 we define using k1. Okay, so I'm going to write L1 over here, I'm going to write L1 over here as L1 as another function. Okay, as we have another function g of h into g of x naught, y naught, z naught. Okay, this one is for the another function x naught, y naught, z naught. Okay, k1 from first function f and L1 from another function g. Okay, using k1 and L1 you can define these values over here, k1 L1 for our k2. Okay, yes. Again we want the L2 over here. Okay, so how we define the L2? So see carefully, L2 I am going to write h using the another function g. Okay, as we have k2 we are going to write L2. Okay, so h keep as it is, only we are going to replace f as a g. Okay, g under bracket. Okay, x naught plus h by 2, y naught plus k1 by 2, z naught plus L1 by 2. Okay, x naught plus h by 2 comma y naught plus k1 by 2 and z naught plus L1 by 2. This one is the value for L2. Okay, yes. So see that these values are important, guys. K1, L1, K2. Okay, need to remember this one. Okay, and L2. These are easy and all are associated with each other. Okay, that you can remember it for longer. Okay, yes. So now we want the required solution like y1, z1 that we found in our previous simple differential equation, y as a final their solution. Okay, so as we have simultaneous differential equation, that means two functions involved, and if two functions are there, that means you will get the two solution. First solution in the form of y and another solution in the form of z. Okay, yes, as we have y and z taking differentiation, so you will get the solution for y and you will get the solution for z here. Okay, yes. So what are the solution that we are getting here? Y, as we consider y as y1, y naught plus 1/2 k1 plus k2. Okay, that we learn already, similar like this we are taking here. Okay, and similarly we are going to write z1 as z naught plus 1/2. Now we are defining here L1, L2, so add L1 plus L2 over here. Okay, yes. So if you want the x1, we know that x naught plus h, we get the x1 over here. Okay, these are the values, guys, you need to remember. This is our entire Runge Kutta method for the second order. Okay, about the fourth order we'll see it in our next lecture. Okay, so I just want you all to know about the Runge Kutta method for solution of a simultaneous differential equation. Okay, these are the initial conditions that we learned in our previous part. Okay, so in this part we consider simultaneous differential equation, where independent dependent variable I explained here with their step size and the starting points. Then I explained here Runge Kutta method for second order, where I define k1, k2, L1, L2, first solution y1, second solution z1. Okay, so this is our entire method. So if you want to note it down these points, you can pause the video, guys, and note down these points. These are important for your understanding. Okay, this one is the Runge Kutta method for second order. For the fourth order Runge Kutta method for our simultaneous differential equation, guys, we are going to see it in our next lecture. Okay, so I hope you all have understood my entire today's lecture. Even after if you have any doubt, any difficulty, confusion, let me know, guys, in my comment section. And if you are interested to see similar videos, guys, go and check in my I button as well. You can see it in here in my description box. You will get the entire playlist there. Okay, so I hope you all have understood my today's lecture, guys. So if you have any suggestion, just let me know. Your all suggestion, anything, it is always welcome here in my channel. Okay, so thank you everyone. Thank you for my today's lecture.